In this section, I will teach you some key concepts behind state estimation algorithms, enough to support system analysis and hardware design. We'll take about a minute in this slide to recap what you saw in my BMS functions video. Measurements of the cell voltages, cell temperatures, and battery current feed into state of charge estimation. State of charge estimation underlies the range or capacity estimates displayed to the customer. It has a highly visible output. The state of charge estimate and some of the baseline measurements feed into two other state estimates, namely state of health and available power. State of health may not directly tie to any system actions. Power estimation, on the other hand, directs the charger as to what charge rates are acceptable, and directs the motor or inverter or other load as to how much current they may draw. The algorithms behind BMS actions are often simpler than state estimation, and we'll discuss some implementation nuances in other lectures. In this lecture, we will focus on state estimation algorithms, a precursor to designing hardware to support them. Let's start with state of charge estimation. Conceptually, we have two ways to estimate state of charge. First, we can simply integrate over time. We know how many amps are flowing through our battery current sensor, and we can integrate those amps over time to get amp hours. This is analogous to measuring the flow rate, measuring the time duration, and multiplying the two. Second, let's recall from the cell behaviors lecture that the open circuit voltage of a cell is directly related to its state of charge, and that relationship is also a function of temperature. We can measure the voltage and temperature and look up the corresponding state of charge. This is analogous to looking at the lines on a measuring cup, measure the depth, and look up the correspondence between depth and vessel volume. The tricky thing is that voltage has a relaxation time. After a current pulse, the cell voltage requires time, possibly hours, to relax. This is not exactly analogous to water sloshing after being poured because the underlying mechanisms are quite different, but whether we measure the voltage of a battery cell or lines on a measuring cup, we must wait for the system to settle for an accurate measurement. We must wait for the pack to be well rested, for the measurable cell voltage to closely approximate the open circuit voltage. A critical piece of estimation from voltage is that we need good characterization data to inform the mapping between voltage and state of charge. In the next slides, we'll talk about these two methods and also how to combine them. Let's talk about current integration first. We can integrate the current that flows into and out of the battery pack to calculate how many amp hours of charge are in the battery. This is a good method for state of charge estimation while current is flowing, when the voltage is not settled. Unfortunately, any offset error in the sensor is integrated along with the signal, and thus the total error grows with time and without limit. Let's take a look. Let's use the Ania 240 current amplifier as an example. This is an excellent high-precision sensor with only a 25 microvolt offset error. Let's say we've designed for a 200 amp hour battery for an application that may draw continuous current of 100 amps, and we've chosen a 250 microohm shunt to keep the power dissipation in the shunt to a manageable 2.5 watts. You might see numbers roughly like this in an electric car or home solar battery. That 25 microvolt offset voltage error translates to a 100 milliamp offset current error. And now, imagine that we leave this pack unused for 2 weeks. There's zero actual current flowing, but our current sensor keeps reporting 100 milliamps. We keep integrating 100 milliamps, and by the end of 2 weeks, it looks like we've added or removed 33.6 amp hours. Every day, the BMS sees a change of 1%, though in reality, the state of charge is constant. In many applications, we can accept this rate of error accumulation over an hour or two, but not over days. We need something to correct for that offset error. Let's review a few key points from the lecture on cell behaviors. The open circuit voltage is a function of state of charge, which is key to using voltage to estimate SOC. This relationship changes with temperature. It is also slightly different in charge than in discharge. The cell has impedance, which means the terminal voltage will change as a function of the current flowing into or out of the cell. And the cell voltage has a time-dependent response. We see in this plot that after a current pulse, the voltage takes time to settle. These concepts are important to understanding how to use voltage to estimate state of charge. Now, let's talk about how to use cell voltages and temperatures to estimate state of charge. We can characterize the cells carefully to create a lookup table or a model, and then use the real-time measurements of cell voltages and temperatures to look up or calculate the SOC estimate. The beauty of this is that error does not accumulate. If we have good characterization data and accurate measurements, our error can be quite small. Unfortunately, an OCV measurement requires zero current for a long time, possibly hours. While current is flowing, the cell voltage is not equal to OCV. We can try to estimate OCV from the unrested cell voltage measurement, but that's hard to do accurately. So, this method provides mediocre accuracy while the application is active, while current is flowing. A second caveat is that this method gives us state of charge as a percentage. To tell the user how far they can drive their car or fly their drone or operate their house, we need amp hours. If the cell is aged, its total capacity may be significantly smaller than its original nominal capacity. So we need some secondary source of information to accurately translate percent to amp hours. Still, for some applications without stringent requirements for state of charge estimation accuracy, voltage alone may suffice. For example, if a cell phone or tablet incorrectly estimates its available capacity, the consequences are minor. Maybe it's not worth increasing the cost of a small device to improve state of charge estimation beyond what's possible with voltage alone. Here's an example of using only voltage from Professor Plett at the University of Colorado in Colorado Springs. In the plot, the orange line is the true state of charge for a real battery, and the blue curve is the SOC estimate using only the voltage and a very simple algorithm. The algorithm simply measures the cell voltage, V of t, and looks up an SOC versus OCV curve. This assumes that the open circuit voltage is equal to the measured voltage, a poor assumption with correspondingly poor results. You can see that the SOC estimate is noisy, and let's be honest, this is too noisy to be useful. If you look closely, you'll notice that between every step are a few minutes during which the true SOC is flat. Flat SOC means we're neither charging nor discharging, zero current. And you can see that during this time, the blue SOC estimate approaches the orange true SOC. This shouldn't be surprising. This is what we expect. When current is flowing, the cell voltage measurement V of t does not equal OCV, and so using V of t to look up a point on the SOC versus OCV curve gives a poor result. With zero current, the cell voltage measurement V of t is close to OCV, and with time, the external cell voltage decays to approach the OCV. So, the same lookup gives a much better result at the end of the zero current interval. You may recall from the lecture on cell behaviors that the cell voltage plummeted during a current pulse and decayed back to a stable voltage over time. We're seeing the impact of that voltage behavior in the SOC estimate. Let's look at the pros and cons of the two methods we've discussed. What do you notice that might make these two methods complementary? I notice that one method is problematic when current is flowing, while the other works just fine in the presence of current flow. If we can mix the two types of information well, we can cover both scenarios. Current integration error accumulates, and OCV can provide the reset to ground truth. Estimation from OCV tells us a percentage, and current integration can fill the gap to converting that into amp hours. Each method provides a means to counter the other's greatest weakness. So, let's talk about how to use information from both these complementary measurements together. Here's a simple algorithm using both voltage and current as inputs, which may suffice for the prototype phase and in some applications. Stop charging if any cell reaches its maximum operating voltage. And stop discharging similarly if any cell reaches its minimum operating voltage. At both those points, reset the state of charge estimate to 100% or 0% respectively. While the application is running, the voltage signal may be quite noisy, both due to the switching of the motor or inverter and due to the IR drop of the cells. In that regime, use current integration to estimate state of charge. This is a very rudimentary sensor fusion algorithm. Some applications have a regular or frequent rest period. For example, a stationary energy storage battery may expect to charge daily midday, then power the house in the evening, and be in a quiescent state through the latter half of the night. Similarly, a drone may spend substantial time resting on a shelf. Many applications actually expect a substantial resting period. A simple algorithm is to estimate state of charge by current integration anytime the battery is not rested, which in this example means during the day when the battery is charging, and in the evening when the battery is powering the house. When the BMS notices that the current has been zero for more than some hours, the BMS switches to assuming that the cell voltage corresponds to the open circuit voltage and estimating SOC by OCV. Here's a third example of a sensor fusion algorithm. This one based on a very simple cell model. The model includes an IR term. The model incorporates a constant cell impedance R0 and estimates OCV as being the measured cell voltage V of t minus the measured current I of t times the cell impedance R0. The plot on the right is from Professor Plett, and you can see how the SOC estimate follows the true SOC more closely than when Professor Plett used voltage alone. This still isn't very good, but may suffice if we can do some filtering or averaging and can tolerate the corresponding time delay. If you look closely at the moments where no current flows, as we saw before, the SOC estimate approaches the true SOC. This is because when no current flows, the terminal voltage approaches the open circuit voltage. Better algorithms for state estimation are model-based, iterative, and involve matrix math. These methods estimate unobservable state variables, like state of charge, from observable variables, like cell voltage and battery pack current. These methods work in the presence of noise or measurement errors. You can think of them like this. Measurements at time k are the input. For a BMS, these might be the voltages, temperature, and current at time k. Then, a bunch of matrix math happens and out pops out the state estimate, such as state of charge. We won't go through all the math in this lecture. We will go far enough for a conceptual feel for some key aspects. The Kalman filter is the most famous in this family of methods. The inputs are often denoted as Z of k, where k indicates time. The output is the state estimate, such as state of charge, often denoted as x hat of k. The hat indicates that this is an estimated quantity. Both zk and x hat k can be vectors, that is, they can contain multiple values. Unlike the previous algorithms, the Kalman filter quantifies uncertainty. The sensor uncertainty is an input to the filter. This might be big if we have a noisy sensor, or small if we have a low noise sensor. And the filter outputs an estimate of uncertainty in the state estimate. Both the state estimate and the uncertainty estimate from one step are fed back into the next step. Inside the Kalman filter is an assumption that the system is linear. Other filters extend this method to allow for nonlinearity. The implementation is usually described by matrix math. Here's a more detailed description of the steps of a Kalman filter. You can write this all as one equation, or as 2 steps, or 3, or 6. The way the steps are broken up is a little arbitrary. Let's start with the initialization step. At time 0, the state estimate is initialized. The algorithm requires a starting number. The predict step predicts what the state and uncertainty will be at the next iteration. The predicted state may include the measurements. The predicted state and uncertainty are fed into the update step, along with new measurements. In the update step, these two are combined. We combine old information in the form of the prediction with new information from the measurements. The update step outputs the state estimate and an estimate of uncertainty. These estimates are the outputs of the algorithm. Measurements and sensor uncertainty in, state estimates and uncertainty out. Some key features of the Kalman filter approach are that it's iterative. We need to store only the state estimate and the state prediction. We don't need to store any older information, which is nice for embedded processors with limited memory. The Kalman filter embeds a system model, part of the predict step. For a BMS, that's a cell model. How well we characterize and model a cell plays into the quality of the prediction. And it's designed to work with noise, both process noise, which is noise in the system itself, and measurement noise, like sensor error. Notice also that any inaccuracy in the model will appear like process noise. That's important because it means that even with an imperfect model, the Kalman filter will converge. I'll also point out that the way I use the word noise here may grate on a physicist's ears. For example, the deterministic voltage spikes caused by a motor controller switching isn't noise per se as a physicist would define noise, but many engineers will call that switching noise. We won't go through all the underlying math, but in the next slide, we will take a closer look at the state update equation. The state update equation is a core step in the Kalman filter math. To estimate the current state, we take the predicted value of the current state, which we calculated in the previous iteration, and add to it new information gained from the present measurement. The new information term is called the measurement residual, or the innovation. To be precise, the innovation is the difference between the present measurement and a prediction from the previous step. The weighting between the previous estimate and the new information is set by a gain factor, the Kalman gain. Each of these parameters has a mathematical representation, and this is the state update equation. Before we move on, let's take a closer look at the Kalman gain. This factor defines the trade-off between response time to new information and noise sensitivity. A gain factor emphasizing new information will be sensitive to noise. Outlier measurements will significantly nudge the estimate. A gain factor that weighs the prior state heavily will be less perturbed by noisy outliers, but with a delayed response to fast changes in the signal. If we have a low noise sensor, we may want to weight its measurements more heavily than if we know that we have a noisy sensor. And the Kalman filter does just that by making the Kalman gain a function of uncertainties. The Kalman gain calculation incorporates the uncertainty of the state estimate and the uncertainty of the measurement. I'm going to stop with the math here. I'm not going to go through exactly how the filter calculates uncertainty, other than to say that the word covariance comes up a lot. Note also that the Kalman filter is part of a family of algorithms. The Kalman filter assumes a linear system. For battery state estimation, the extended Kalman filter is more commonly implemented because the EKF is extended for nonlinear systems, and the relationship between cell voltage and state of charge is nonlinear. The sigma point Kalman filter is more accurate, but conceptually more complicated, which deters people from implementing it. A particle filter uses a different method internally, is more accurate, but often requires more computations, which can be problematic for an embedded microcontroller, such as those used for battery monitoring. The central difference Kalman filter is easy to tune, with only one tuning parameter, h. If you're interested in seeing the mathematical details of these methods, I encourage you to view Professor Plett's course materials. My goal in these slides was to motivate why Kalman filters are useful and to illustrate the key ideas. If you're interested in following the math to the end, KalmanFilter.net explains Kalman filters clearly and intuitively. The math is masterfully presented with a gradual buildup from intuition to examples and finally the complete equations, which I've omitted. If you want to implement a Kalman filter for battery management, refer to Professor Plett's course materials, including octave code. It's also important to note that state of charge estimation is easier for cells with a steep OCV-SOC slope than for cells with a shallow slope. And typically, NMC cells have a steeper slope than LFP cells. For this NMC cell, every percent change in state of charge corresponds to a 4 to 8 millivolt change in cell voltage. That's a change that most battery monitoring chips on the market can detect. But for an LFP cell, a 1% SOC change corresponds to only 1 or 2 millivolt change in the voltage. That's tiny. That's within the error of some battery monitoring chips, and smaller than the time-dependent depolarization due to recent current flow, and much smaller than the switching noise in many applications. The voltage of an LFP cell is nearly useless for state of charge estimation from about 25% to about 90%. The details of how a BMS algorithm weights cell voltage information and battery current information will be quite different for LFP cells with their flat curves versus for cells with steeper slopes. Notice that the LFP slope gets quite a bit steeper at the top and bottom of charge. A cell voltage measurement with, say, 5 millivolt accuracy can still provide us with what we need to prevent overcharge, part of managing for safety. The requirements for cell voltage measurement accuracy to support safety are different from the requirements to support state of charge estimation. Let's summarize what we've learned about SOC estimation. The battery current measurement provides best information during charge and discharge when current is flowing. The cell voltage information provides ground truth. It is the ultimate limit on SOC estimation accuracy. Combining current and cell voltage information is powerful. Methods for sensor fusion provide more optimal results than simpler algorithms. Extended Kalman filters are one example of an iterative, model-based method for sophisticated SOC estimation. The slope of the OCV-SOC curve affects usefulness of voltage information. In practical terms, it is more challenging to estimate state of charge of LFP cells than of cells with steeper curves. Safety and SOC estimation may entail different hardware requirements. This completes the section on state of charge estimation. Next, we'll discuss state of health, or, in other words, capacity fade. You may recall from the lecture on cell behaviors that lithium-ion battery capacity degrades with time, calendar aging, and also with use, with charge-recharge cycles. As the cell ages, we cannot assume that the cell's capacity equals the nominal capacity when new. Let's start with the optimal way to assess cell capacity. This is what a cell cycler does, a specialized instrument without the cost or time constraints of a consumer product. First, the cycler discharges a cell to 0%. The cell manufacturer specifies what voltage corresponds to 0%. Then, the cycler charges the cell to 100% while very accurately measuring the charging current. Then, we sum how much charge we put into the cell. Because the cell cycler implements very accurate measurements of current and time, the calculated total cell capacity is also very accurate. We can do the same for measuring capacity in the discharge direction. Discharge the cell fully, measuring current and time accurately, and again, sum the total amps to get the total capacity in amp hours. A BMS has two measurements related to capacity: cell voltage and battery current. Cell voltage changes with state of charge, but whether the total capacity is 90 amp hours or 100 amp hours, the shape of the curve is the same. We cannot determine total capacity from voltage alone. Like the cell cycler, we must rely on the battery current measurement. Because the current measurement in a product is unlikely to be as accurate as in a lab instrument, in the field estimates of total capacity are typically less accurate than in a lab. If we have an application that sometimes cycles from empty to full, we can do exactly what the cell cycler did. Start at 0% and charge to 100%, measuring current and integrating the total charge. Unfortunately, many applications don't work like this. Hybrid cars often cycle between 40 and 60%. Fully electric cars often cycle between unpredictable parts of the range, sometimes stopping at a consistent end of charge, but rarely discharging to the same point. We can do something pretty similar though. We can look at how much total charge we put in during a single charge or discharge cycle based on the current from our battery current sensor. We can look at how much the state of charge changed during the same cycle. Importantly, we need to use the state of charge estimate from OCV. So, we need to do this for a cycle wherein the battery rested at both the top and bottom of the cycle, so that our measured cell voltage corresponds closely to the open circuit voltage. Finally, we can combine the two to calculate what the total battery capacity must be. Let's consider how the error in this capacity estimate differs from our nearly ideal cell cycler measurement. Current sensor error affects the final estimate directly. If our current sensor has a 1% error, then our total capacity estimate also will have a 1% error. Error in the time measurement also directly affects the final estimate. Error in the cell voltage measurement has a complicated and nonlinear impact. Cell voltage measurement error affects the state of charge estimate. How sensitive SOC estimation error is to cell voltage measurement error depends on the slope of the OCV versus SOC curve, and we'll look at that more in the lecture on value of accuracy. To summarize then, estimating capacity fade involves both current and cell voltage measurements. These feed into a calculation of the total charge in amp hours added or removed during a single charge or discharge cycle, and an estimate of the corresponding change in state of charge. These two calculated quantities allow us to calculate the total present battery capacity. This is a useful quantity for the application software since it relates to how much energy is available to the user in a single cycle, from full to empty, or empty to full. State of health is often defined as this total present battery capacity as a fraction of the initial nominal capacity when the cell was new. Okay, got that? Let's move on to power estimation, which relies on estimating the increase in cell impedance as a cell ages. We saw in previous lectures how cell impedance increases as a cell ages and how that can be modeled with a series resistor. Let's first quickly review what this has to do with power estimation, and second, how we can estimate the series impedance in the field. As you may recall from the lecture on cell behaviors, when we apply a load current to the cell's terminal voltage decreases proportionately to the load current multiplied by R0. Since we must stop discharge when the cell's terminal voltage reaches its minimum operating voltage, for a given load current there is some residual capacity that we cannot access. Or we must reduce the load current, reduce the power. With an increased R0, the battery can provide less power. To provide a good estimate of available power for an aged battery with an increased internal impedance, the BMS must estimate the magnitude of this IR drop based on an estimate of the battery impedance. So, how do we estimate this internal impedance? At a point when the application experiences a step change in current, we can measure the battery current and the corresponding voltage change and use them to calculate the battery impedance. Equivalently, we can write the math like this. The estimated battery impedance is equal to the difference of the voltage measurements at two different moments in time divided by the difference of the current measurements at those same two moments. Note that the cell resistance varies with temperature and varies with state of charge. So, we need to either opportunistically repeat this measurement at various temperatures and states of charge, or we need a model for R0 that we update with whatever subset of measurements we've opportunistically captured, or some hybrid approach. You can imagine that the algorithm design and details of the firmware implementation could become quite sophisticated. Let's look at how complicated this is to implement in practice. Here, we see the cell voltage and battery current recorded during a 3-hour drive cycle. You can see how much the current varies and the corresponding impact on the cell voltage, as well as the monotonic voltage decrease as the state of charge drops. Let's zoom in on a shorter section. We can opportunistically pick out some abrupt current steps where we can measure a delta V and a delta I and calculate cell impedance. But we also have some current steps that aren't as ideal. Deciding which current steps to use and which to discard, or, better yet, Kalman filter style, to which to assign high certainty and to which low certainty, is an important implementation challenge. We're going to stop here. We haven't discussed implementation details, but you should at this point have a conceptual understanding of the fundamentals behind state estimation algorithms for battery management systems. If you liked what you saw and would like to see more, please let me know.